You could join us online or in person. I'll quickly remind you that we are streaming to YouTube live from Concordia University's For Space, which is located on unceded Indigenous lands here in Tiohtià:ke, Montreal. And I think to get us rolling on time, I will be passing the floor now to Associate Dean of Research and our host for today, Patrick Leroux, and his special guest joins us, Marek Majewski, who'll be speaking on his expertise on solar energy conversion. Looking forward to it. Over to you, Patrick. Welcome back.
Thanks, Anna. Thank you, everyone, for still being here. This is the third hour of science conversations, research and conversation, focusing on the sciences today. We've had many colleagues from pretty much across the faculty come in and talk about their research, and I've had the great pleasure and privilege of being a student again and learning about all the interesting things that you're doing. Marek Majewski is an assistant professor in the Department of Chemistry and Biochemistry. Marek, you work on inorganic chemistry, materials engineering, nanotechnology, solar energy research, and I'll have some questions about that in a moment, and also light-based chemistry. After a BSc in chemistry at the University of Saskatoon, PhD in chemistry as well at UBC, postdoctoral fellow. You were a postdoctoral fellow in solar energy research at Northwestern. You came to Concordia in 2018, so going on 5 years.
Time flies when you're having fun.
Yeah, no kidding. And it sounds like you've been having a lot of fun, and it's been recognized. You've had the Dean's Award for Excellence in Scholarship last year. You're an active member of many research centers, the Center for Nanoscience Research, the Center for Research in Molecular Modeling, as well as the Centre Québécois sur les matériaux fonctionnels. So let's start with an easy one.
Okay.
Can you tell us about your field of research so that I can sort of ease my way in? I know that you work on light being used as a catalyst for fuel. What does that mean exactly?
Yeah, so thank you very much for having me. This is excellent. I'm obviously very excited to be here. So in general, our group is the Solar Energy Conversion Group in the Department of Chemistry and Biochemistry here at Concordia. And our focus is solar energy conversion. And a lot of times when we talk about solar energy conversion, people kind of picture solar panels. And right. That's more in the realm of what we call solar electricity. So we're using sunlight to generate charge and to drive a current and to power whatever electronics we need to power our electrical systems. So our group works on solar energy conversion, but we work on something a little bit different. So what we're specifically interested in is we're taking the energy from the sun and we want to store it in chemical bonds. And so we're really interested in driving these types of processes that we call fuel forming processes. And one that people are very familiar with is taking water, splitting it into its constituent parts, which are of course hydrogen and oxygen, and then using those parts as fuels. So we know, of course, hydrogen is an excellent green fuel. And one of the goals of solar fuels research is to use energy from the sun to drive that process of splitting water into hydrogen and oxygen. So we need a lot of energy to do that, but then we get a lot of energy back from those fuels we generate. And specifically, our group is really interested in designing the materials and the molecules that drive those light capture and conversion processes, specifically in this realm of making these fuels.
And how do you store these fuels? I understand the principle, and you store it through water, through the creation of hydrogen. How stable is hydrogen once you store it? Yeah, are those some of the questions that I guess they're downstream?
Right. No, of course, but these are all very important questions. And so, of course, one of the big issues, with using these fuels like hydrogen is how do we translate them to our existing infrastructure? And hydrogen is, of course, a gas, and we're much more equipped to deal with liquid fuels. And so transitioning all our existing infrastructure to fuels which aren't liquids, like hydrogen, is very challenging. And so there are certainly people working on that. For us, for our research specifically, we're not so much concerned about that. What we're actually even more interested in is driving these same reactions. So hydrogen is just one example, but we're interested in driving these reactions where we can actually generate liquid fuels. So another example of that is if we can take carbon dioxide and we can use sunlight to reduce that carbon dioxide into some sort of fusel alcohol. So for example, can we take sunlight and use its energy to convert CO2, carbon dioxide, into ethanol, for example, and then we can use ethanol as the fuel. And because it's already a liquid, it's a lot easier for us to deal with. Now, kind of a second aspect of what we're really interested in is this is the idea of solar fuels that I'm talking about. But one other thing that's really important, we think, is using sunlight to drive other chemical transformations, which don't necessarily give us fuels, but they generate molecules of great importance. So we can use the same chemistry that we use to generate solar fuels, but we can use that chemistry actually to drive processes to make molecules that we can use in pharmaceuticals. So for example, what we call pharmacophores, so the active components of drugs. And these sorts of chemical transformations are very challenging to do in general, and using the sun's energy, we can simplify some of these processes or access more challenging chemistry. So that's another aspect of where we can apply this chemistry, where it's not just purely fuels.
Right, so you're doing this in a lab setting, so it's a very controlled setting. Eventually this needs to translate in industrial terms for it to be viable, obviously. Of course, so you have, it's another conversation that comes afterwards. I'm wondering how much energy does it require to transform, to create these solar fuels, as opposed to, for instance, you clearly differentiated the solar panel technology, which is more, I guess, mechanical. I mean, you create electricity, and then you've got this other technology where you need a lot of energy to create storable energy.
Right.
What is the ratio? And is it worth it ultimately? Yeah,
well, so I mean, that's, there's a very challenging physical chemistry discussion to be had there. But, in the kind of perfect world, what we can imagine is we're putting in, to split water, we're putting in the exact amount of energy that we'll get back when we burn the hydrogen. So that all depends on the efficiency of the materials that we design in our lab to convert that sunlight into those fuels. And so that's obviously one of the major goals of the work we're doing, is to study the processes that happen at the atomic level so that we can maximize that efficiency. So we're capturing just the right amount of energy we need to transform whatever our starting material is, so our water or our carbon dioxide, into a fuel with no need to input an overage of energy.
Right, and the initial energy is there, it's not being wasted, it's not being used.
That's right, exactly, yeah. And a lot of times we lose that energy, if we design inefficient processes, we lose that energy as heat or other complementary processes. So one of our goals, of course, when we're designing molecules and materials for these processes is to really optimize the efficiency of them. And we do that by really understanding kind of the fundamental chemistry processes happening at the atomic level.
Right, and you mentioned two fuels, hydrogen and ethanol. Are there other unexpected fuels that you've been working with?
Well, they're not all unexpected. We have a wide breadth of targets, and these are all challenging processes. And actually, splitting water into hydrogen and oxygen is one of the simplest of these processes. As you want to make more complicated products or fuels, it becomes more challenging, both from an energy input standpoint as well as the chemistry that has to happen. But one of our complementary research thrusts is to take nitrogen, so just dinitrogen, which is a very inert molecule, and convert it into ammonia. And ammonia in itself can be used as a fuel, but it's also a great way to store hydrogen as a liquid, because of course ammonia, we can liquefy ammonia a lot more easily than we can liquefy a gas like hydrogen, for example. So that's kind of a tangentially but also related target for our research.
And this fits within the current liquid fuel infrastructure around
That's
the
right.
world.
Yeah,
Right.
absolutely. Yeah. Yeah. And the idea there too is, like I said, you mentioned storage of something like dihydrogen. You can store it in ammonia, and then you can take ammonia and crack it to release the hydrogen, as well as nitrogen gas. So that's the kind of complementary process to all these other ones that we're talking about.
So I'm seeing multiple implications in what you're doing, and multiple interlocutors. Who are some of the people you're speaking to? I imagine engineers, I imagine physicists. Tell us about how they influence your research design, and also what they might be suggesting in terms of possible outcomes.
Yeah, of course. I mean, obviously everything we're doing in our lab is very fundamental. So we're really trying to understand these processes at their most fundamental level so that we can inform the design of future materials. Mm-hmm. But the reality is our goal is always to take this beyond the bench and to try to contribute to the mosaic of alternative energy.
Right.
And so we do work collaboratively with colleagues both at Concordia within the centers that you mentioned in the introduction. Specifically, I have collaborative projects currently in the new chemical and materials engineering department. So that's a very important avenue for us to be able to take our fundamental studies and start thinking about how we can translate them, obviously, to pilot and larger scale. But we do also work together very closely with physicists. We work together with people who are involved with studying our materials, using spectroscopy, for example, so very advanced characterization techniques so that we can really get the most accurate insight into what's happening in these materials when they absorb sunlight. So we do work together, as my colleague Jean-Ming was mentioning in his conversation. It's a very interdisciplinary area of research, and so we bridge the gap between our knowledge and the knowledge of others through extensive collaboration.
Right, and we had mentioned Jean-Ming's lab with the tire and the multiple projects, and I remember very clearly walking into your lab as well this fall, and it's basically like an open space, right? You have so many colleagues are working on their own research within the same space. So could you tell us a bit about, well, you're in the Science Hub, tell us how this works. How do you carve space for yourself in that environment? What possible cross-contamination, in the noble sense of the term, can be happening?
So we're very fortunate because our group is currently housed at the new Applied Science Hub over at the Loyola campus, which is it's a really beautiful space, beautiful modern lab. And we benefit a lot from having a shared space together with a number of our colleagues in the Center for Nanoscience Research. So specifically, our lab is in a large open lab space, which is what you saw, shared together with Professors Howarth, Nakash, and Capobianco. Mm-hmm. And the beauty of this is that all of these researchers are working on very different topics. And what happens is we have this kind of informal setting where the researchers working in our labs get to cross-contaminate or cross-pollinate, or where they get to discuss their own research together. And I think the beauty of this is what we find is that a lot of the fundamental processes that we're studying translate across these different research fields. And so these researchers get to benefit from the perspective of others who are working on completely unrelated problems, but bring a very different conceptual perspective to the problems that we're working on. So there's a lot of informal interactions that are happening. It's actually, it's quite nice to see. And there are relationships that are formed because of this, scientific relationships that I think will carry and generate a lot of new ideas.
And these informal relationships, are they happening mostly through the students running the experiments in the lab and then bringing this to professors, or is it also happening at a more formal level where you sort of present each other's work on a regular basis within the research center? Yeah,
so our research center is well, first of all, it's composed of a lot of individuals doing some really amazing research. So I I think it is very important for us to interact and discuss our research, and our center leadership is currently working on setting up and coordinating a kind of center research day where we can, in a more formal setting, communicate all of our research to our colleagues so that we can really look at the kind of nuts and bolts of what everybody is doing and discuss it and see if there are potential collaborations that we can build on. So this is certainly something that we're trying to put in place.
Right. And you mentioned earlier that the chemical engineering colleagues are also very much involved with your research. I think they're physically out there as well, right, at Loyola? So
that's right.
Yeah. How does that work?
Well, it's actually a wonderful byproduct of the design of that science hub. So we occupy a floor of the building, and the chemical and materials engineering department occupies the floor below ours. So as you can imagine, first of all, this really opens the door to close collaboration just spatially, so we can benefit from each other's resources. But again, the same sort of kind of informal interaction that happens within our open lab can happen between researchers working across disciplines this way. And this is one of the main reasons why we chose to collaborate with researchers in that new department as well.
Right. You mentioned earlier the sort of happy byproducts of some of the solar conversion into fuels, and I want to come back to that, the idea of molecules being interesting for pharmaceuticals. So this is you've seen this in your lab, or this is happening here at Concordia, or we know about it elsewhere?
No, it's happening at Concordia. So we, in fact, our lab has even published work on driving the formation of some of these, what we call pharmacophores, using the same device architectures that we use to generate solar fuels. We can use that exact same chemistry actually to drive chemical transformations where we can generate these molecules, which are not fuels, but they're useful molecules in other arenas.
Right. So these are molecules that are byproducts, and would harvesting those molecules for further use, could that be integrated into a fuel system?
Well, absolutely. And
Still
so,
popping planes.
Yeah, that's right. Yeah. Well, no, I mean, this is actually a very important observation, because we're putting a lot of emphasis right now on decarbonizing our economy and our overall societal reliance on carbon-based fuels. And obviously this is crucial, it's long overdue. But one of the side effects of this that I don't think people think about is that a lot of our industry relies on byproducts from oil and gas for the manufacture of consumer goods, as well as anything you can think of. So really, there are maybe 5 to 10 kind of raw resources that we then transform into intermediates, that we then transform into chemicals that we use to build everything that you see in front of you, pick anything. And so one of the realities, if we decrease our oil and gas exploitation, as we should and as we're planning, is that we're going to have to find different ways to make these and manufacture these chemical intermediates. And so this is where this type of chemistry really plays a role, is now we can use solar harvesting to refine some of these raw materials to generate these chemical intermediates that then we can take and build whatever our consumer good or our pharmaceutical or whatever that we need. So a very important part of the decarbonization conversation is how do we generate these intermediate chemicals that we need to generate whatever products we need. And this is one place where we're trying to really insert our expertise.
It's fascinating. Yeah. Are there carbon alternatives, for instance, for plastics or for all of these materials you're alluding to that come from fuels, essentially carbon-based fuel? Do we have those alternatives yet? Are we looking into it?
Well, I mean, there are many people doing really, really wonderful research on replacing plastics with biodegradable or bio-based products. So certainly the technology is there. There's an argument for some maturation that needs to happen, but there's no real reason why we can't generate alternatives at this point.
Right. Yeah. Recently, there was an article on your research in the Concordia Alumni magazine, which what was happened to be on an ambassador's desk one day. So we ultimately had 5 Nordic ambassadors coming to Concordia, and they went through you, and you had the foresight, and I think the openness of reaching out and wanting to make sure that they spoke to as many colleagues as possible. Do you want to tell us a bit about this, and like what were they interested in? What did they come for, and what do you think they got from meeting
Yeah,
us
I mean,
here?
this was a really exceptional event. It was actually a very it was really cool.
Yeah, it was,
Probably
yeah.
for sure one of the more exciting things that's happened to me in the time that I've been here. But we had been asked for a comment for an article about the renewable revolution in Concordia University magazine. And it caught the eye of one of the advisors for the ambassador to Iceland. And it turned out that they were coming, the Nordic ambassadors were going to be on a visit to Montreal, and they wanted to come to Concordia to discuss sustainability science.
Mm-hmm.
And so they reached out to myself as well as a few of the colleagues who were in the article, and I immediately jumped on the opportunity, and I said, of course, come visit us. There's amazing sustainability science happening at Concordia. And so with your support and your office's support, we were able to host the Nordic ambassadors here at Concordia. And they came to discuss some of the sustainability initiatives that they have in their respective countries, which are all extremely impressive, and there's a lot that we can learn from them. But they were especially interested in what we're doing here at Concordia, and I think certainly we left an impression on them both from the applied and the fundamental side, what we're doing. And what we're really looking for is potential links, but we're also looking to see what works, what things work that they're doing, and how can we translate them to what we're doing. And they're looking to see what we're doing and how they can translate it to what they're doing. And I think probably one of the most interesting outcomes of all of this for me, beyond obviously meeting these very influential individuals and hearing about what the Nordic countries are doing, is that I was able to connect with some of the sustainability community here at Concordia, which is extremely extensive, bridges faculties, and there are some people doing some amazing sustainability science. We certainly have a critical mass for it here at Concordia, and having everybody in the same room together with these individuals really served to highlight how much of this really amazing science is happening here.
It was a truly fascinating moment where we had engineers, scientists in the natural sciences, social sciences as well, colleagues from JMS Business School, someone from journalism. And this conversation actually was happening, prompted by their presence, but they also provoked us a bit, right? They came in with a statement, and they said, here is how our 5 countries position themselves with regards to sustainability goals. We'd like to know what you're doing, and perhaps you can do better.
Well, I mean, I think clear, right? Absolutely. I mean, I think one of the things that was really emphasized in this meeting was, they have so many collaborative initiatives there, cross-national initiatives, and they're really tackling what is really a grand challenge. They're tackling it in a very unified fashion, and very assertively as well. So I think there's a lot to be learned from their approach, but I think it also did, their kind of engagement with what we were talking about, I think also highlights that we're doing some really good stuff here as well too. And so I think we need to continue on that road and continue to look for ways to work on this grand challenge more collectively, right? So this idea of addressing climate change, this isn't a one-person event, right? This needs to be a collective grand challenge that's met by all the researchers and politicians and policymakers, and everybody needs to work on this together. We all need to pull in the same direction, and I think that was certainly one of the things that was emphasized by this meeting as well.
No, it was interesting, and a mixture of politics and policy and science happening at once. Yesterday, the federal government just announced its budget, and there's a massive investment in, I guess, what we could call the electrification of society. How does your research fit into this? Because you're not talking about electrification here. You're talking about the conversion of solar power, solar energy into fuels. How do you navigate this, and where do you find your place also in these new frameworks, right? Is electrification the only framework we can think within, or are there others as well?
No, and I mean, I think you see that in the federal budget as well. So a major component of the federal budget, were tax initiatives for actually green hydrogen and green ammonia, actually. And I think, it's pretty clear that our current federal government is betting big on the hydrogen economy, not just on electrification. But both of these things go hand in hand, so we can envision kind of a future where both solar electrification is working together with this solar fuels process, because ultimately there's a lot of fundamental overlap there. So I think, we fit very well in this framework. We're not specifically working on green hydrogen all the time, but, the processes are similar. We're very interested in ammonia. And, I think there needs to continue to be this investment in the R&D for these technologies. So I think this is a very nice thing to see in the budget.
Right. What stimulates you the most in terms of research? What kind of interactions? What kind of problems? What kind of comments or requests?
Well, I mean, at the heart of it, I just think science is really cool. So I am extremely fascinated by this idea of making and breaking bonds, because this is, it's a problem that we can't see with our eyeballs, but it's this incredible fundamental phenomenon. So at the core of it, I mean, I just think science is really cool, truthfully. But I am also a huge outdoors person. I like being outside, and I think protecting the natural world and protecting our environment is exceedingly important. So, and I think science, even fundamental science, has a huge role to play in this. And so, from a really practical standpoint, I guess I love going canoeing, I love being outside, and I want to make sure that I can continue to do that for as long as possible. I want to make sure that the next generations can experience this as well.
Right. And speaking of next generations, you have students in your lab.
I do.
What are some of the concerns or questions, desires as well that they're expressing in terms of research, and how are they pushing you?
Yeah, well, they push me in all sorts of different ways. I mean, it's very exciting to work with people who are also very dedicated and invested in this topic. And I think one of the things that's really important is that we keep looking at the big picture, because we often focus in on very narrow fundamental processes. But yeah, I'm very fortunate to work with a group of students here who also are very interested in this type of science and interested in the same things that I'm interested in. And there are very simple interactions that often get me really kind of get me going. They send me new articles on new science that has just come out, which is related to ours. And then we immediately start asking, why can't we, or how can we apply our knowledge to this problem that they're talking about? So that's just an example of a very kind of basic but routine interaction that we have.
Right. And how do you manage, I guess, to keep up with the ever-evolving, ever-changing science?
It's a challenge. But again, so actually that's a great question. I mean, for me, sometimes it's about carving out time and making sure that I put everything else aside and I spend a little bit of time with the literature and with the news and see what's going on. But I do actually rely a lot on my colleagues, and I do rely on the researchers who work in our lab to also kind of keep me up to date. And they're very focused on their specific topics, which are quite broad. And they often are the ones that are keeping me on my toes and keeping me fully updated on what the latest advances are in our field.
Right. Yeah. And when you sort of project yourself in the future, where would you like to be? Where would you want your research to be in 5 to 10 years?
Oh, well, I have a lot of dreams in this regard, but there's some very crucial problems that we're trying to solve, and I think what would be really, really cool for us to see is to see one of our devices or one of our materials being used on a larger scale. So potentially in a pilot facility, potentially for green fuel or one of these other chemical transformations that we've been talking about. So seeing it go beyond the bench, I think, would be really, really magical.
Right. So what is needed for you to get there?
Yeah, well, so luckily we do have good collaborations that I think can take us there. We're always looking for industrial partners as well who we can kind of get a good feeling for what their exact needs are to take something from the lab and to apply it in their processes. So I think either a specific industrial partner or a collaborative industrial partner would be particularly beneficial for us, and we're actively looking for opportunities to work with people both in Canada but abroad as well.
Right.
Yeah.
Like we know, for instance, Bombardier is working on
Yes,
hydrogen fueled planes.
Yeah.
So how would you broach that possible partnership, for instance? Because they probably have their own teams working on this.
Yeah.
How do you do this?
Yeah, well, we would look for if there's a specific part of this technology that they're using that maybe isn't as effective or efficient as it could be, and how can we insert our knowledge to repair that part of the process, to get them to where they need to be fully applicable, I guess. So
Right.
we have excellent fundamental knowledge in these, as I keep saying, the chemistry that's happening at the atomic level. And so how can we translate that to their process, and specifically how can we use it to upgrade parts of their process so that they can kind of get the max return on their on what they're doing.
And I guess I've been insisting on the practical applications.
Yes,
and if we sort of switch this around, and what are you learning in the fundamental science side of things from these various requests, demands, and societal needs?
Yeah, I mean, well, so, at the very basic level, one of the things that we're really interested in is what happens to molecules when they absorb light energy. So what happens to a molecule when it absorbs a photon of light from the sun? And then if we can follow that process of what's happening in that molecule once it absorbs that light energy, we can translate that to then a device. So we can, once we understand what the molecule is doing, we can translate that to how we can optimize a device that absorbs sunlight and then drives one of these fuel forming processes. So for us, what's really interesting is to see how molecules and materials behave once they absorb this massive amount of energy from the sun. And there's various transformations, structural, and there's also electronic transformations that happen that we're really interested in probing.
Right. And do you conceive of and build those devices? And what do you mean by device?
Yeah, so, well, to be extremely specific, I mean, we build what are known as photoelectrodes.
Okay.
So we build them on a lab scale, so they're about 1 centimeter by 2 centimeters, and what they have is an active layer of material on them that absorbs light, and on that surface where that light is absorbed, that's where all the chemical transformations happen, where the fuel is generated. So we do make those in our lab. They're a very crude approximation of what an actual commercial device would look like. But the fundamental processes are going to be the same, whether it's on our tiny device or on a larger device. It's just, then it becomes a problem of how do we translate what we know about the tiny device to the big device, right?
And this is where you need partners.
That's right, absolutely.
Yeah. And are those partners generally aware that this is something they should be looking into?
Yes, no, of course, there's a wide breadth of people working on this problem from many different angles. And I think the stuff that we're working on is going to be applicable in very specific processes. So, we're looking for a partner that's interested in those processes as well.
Great. Now, this is absolutely fascinating. I'm learning so much from you and from the research you're doing. If I were to, I guess, so we talked about the processes, we talked about the issues. I'm curious to know about your I guess your experience as a researcher also. It seems like you've been tapping into the various resources that are available to you. You're involved in the Nanosciences Research Center very actively. You're reaching out to colleagues in other departments and other faculties. How what are the opportunities? What are the concrete challenges, but also opportunities that you're facing in your lab, in your research here?
Yeah, I mean, well, there's a number of challenges that we're facing. In general, in terms of opportunities, I mean, I think one of the really beautiful things ties back to everything that we've talked about so far is that, you know, people have realized that this is a collaborative problem and it needs to be addressed from all sorts of different perspectives and different scientific perspectives. So there's a big drive to do collaborative science, and we see that at the federal level in Canada as well too. So there's a lot of financial support for partnerships between academia and industry. And this is, of course, really exciting because it should hypothetically help us translate what we do on the fundamental level to the more practical level. In practice, it's a little bit more challenging because, as we've been talking about, you need to find a partner that you can work together with. So this is something that's particularly important, I think. You know, we have this interesting and very exciting and invigorating community here in Montreal. So there are a lot of researchers across a lot of institutions working on this problem and similar problems. So there's a lot of crosstalk between the different institutions here as well. And for me, that's been one particularly engaging part of being in Montreal, is being in this broader community. So we have a lot more support in our specific science as well, too.
Right. And across the 4 universities.
Exactly. Yeah, exactly. So you know, there are resources that other universities have that we don't have, and that we have that they don't have. And it's a very open community in terms of sharing that you know, both ideas and sharing you know, concrete practical resources like instruments, for example. And so as a researcher, that's particularly valuable because we get to kind of maximize our own resources by taking advantage of everything that's around us as well too. So we can really focus on specific things that we need to improve and work together with others on other things.
Right, and you mentioned this push towards interdisciplinarity, which I think is extraordinarily healthy. But how do you negotiate the real need for time and effort and investment in the fundamental science side of things, and this desire and push towards more interdisciplinary connections, right?
Yeah.
Time is finite.
Yeah, no, for sure.
So
yeah.
how do we do this?
Yeah, well, I mean, you know, so I agree with you. Our time is constantly getting chopped up, and we have less and less time for these sorts of interactions. But I think it's very important to look at events, both regional and national events, where we can connect with fellow researchers and people working on similar problems. And, you know, a lot of it comes over kind of almost informal discussion where you see somebody that you know is working on something that's related or tangentially related to what you're working on, and then it becomes a question of, you know, hey, this is a really interesting thing that you're doing that could really augment what we're doing, and then from there, what can we do? And then this is where you start looking at other supports, so institutional and federal support, financial support, to kind of build these sorts of connections.
Right, so not necessarily conducting research side by side on every front, but
Right.
finding opportunities
Right.
for those connections to happen.
Yeah.
For opportunities to learn from each other.
Yeah, and also translating what we know to you know, other fields is very important as well.
Right.
So we were last year awarded a NOVA grant from NSERC and FRQNT, and this is a collaborative grant where I'm working together with researchers at INRS here in Montreal, specifically with Annie Castonguay, and a researcher at McMaster University in Hamilton. And we're translating what we know about the materials that we make that capture light, and we're translating that to biosensors now. So what we're doing is we're using the same sort of chemistry that we use for fuel forming processes. We're actually using that to detect biomarkers and disease biomarkers in devices that don't generate fuels, but translate those same fundamental processes to something where we can use this in a whole completely different realm. So that's another, I think, very important aspect of what we're doing, is looking for ways to translate our knowledge to other problems as well.
Yeah. 3 hours ago, I started the day in conversation with colleague Dr. Gauthier, who was talking about biomarkers.
There you go. You've come full circle.
You've brought us back. I want to thank you for this conversation. You've been extraordinarily generous and clear in presenting the research you do and translating its fundamental importance. I'm excited to see what's going to come out of it in the future. So I'll open up for questions in the audience or online, if there are any. Yes, we have one question from a fellow chemist.
I was going to say from a colleague. This is going to be tricky.
You can take that one.
Hi, Marek. Thank you for sharing your research. So my question is related to what you mentioned. You like the kayaking in outdoors. So I wonder, like, when you are in the sun outdoors, are you still thinking about how the solar energy breaking the bond, or does the sunshine outdoor give you some period, like keep you away from the solar energy, like a science?
No, of course. I mean, when I'm out in the sun, I'm thinking about it breaking my bonds, truthfully. So, I mean, this is a good moment to really emphasize the importance of sunscreen, particularly mineral-based sunscreens that absorb the very harmful high-energy UV rays. So, of course, the sun produces an immense amount of energy. So make sure you protect yourself and your loved ones from it. But outside of that, I am, of course, also thinking about that energy and how we can harness that energy to use it to drive all these processes I'm talking about. But that was an excellent moment for a good public service announcement. So wear your sunscreen.
But there's been research in sunscreen by your colleague that suggests that there are chemical reactions that aren't necessarily good for us as well, right?
Absolutely. Yeah, so that's a very fascinating, very interesting field of research where what's really interesting about it actually is it's the same fundamental chemistry happening in sunscreen that we harness to drive these chemical transformations, right? So we absolutely are aware of that. We need to be thinking about that too. Yeah. Thank you for the question.
Any other questions? Yes.
I was just curious because I don't actually encounter this like field of research often in terms of being more in the biology side of things. How did you first fall into this like world of light? Like, what was there a spark moment? And
well, thank you very much for a very excellent question that I think about all the time. I mean, I think a lot of it comes from my overall love of the outdoors and the environment, the natural world, and for trying to find ways to protect that natural world. So because of that, I kind of by momentum, let's say, became interested in alternative energy. And you know, there's a very interesting link between organic chemistry and alternative energy, and I was always very interested in organic chemistry, so things kind of fell into place one after another like this. But what I wanted to say, actually, to address the first part of your comment, we don't ignore the biology aspect of things either. So we do have ongoing projects in our group where we're using biology. So in fact, we're using specific bacteria to drive some of these fuel forming processes for us, because nature has benefited from a lot of time in evolution to really refine these processes. And of course, we're aware of that. We're inspired by that. So we try to harness biology as well to do a little bit of this work for us.
Any other questions? Good. Well, thank you so much for your time and the conversation. I'm really looking forward to finding out more about your research. We'll keep in touch.
Thank you so much. It's been a pleasure to be here. Absolutely. Yeah.
I'll mention that the next series of conversations will be happening on Friday, May 19th. Axel Watanabe, an assistant professor in economics, will be talking about the agglomeration and geographic mobility studies he's involved in. That's at 10 a.m. on Friday, May 19th. At 11 a.m., Matthew Barker, an associate professor of philosophy, Francesca Scala, professor in political science and associate dean of graduate studies, as well as David Secco, professor in journalism, will be looking at science, but through the eyes of the humanities and social sciences. So I'm looking forward to seeing you there, May 19th. Thank you. And thank you again to ForSpace for housing us. This is an extraordinary opportunity. We love your professionalism. And thank you also to the Dean of Arts and Science for allowing me to be a nerdy student, like really intensely for these conversations and pull me out of the office and into these essential conversations.
Absolutely.
Take care. Bye-bye.